Schwarberg here, lesson 2-2, part B. In this video, we're going to talk about limits at infinity, okay? And the main thing that you need to think about with limits at infinity is the horizontal asymptotes. And I know this is kind of murky. We touched on this in Accelerated 3, but we're going to jog your memory on horizontal asymptotes and how to determine them, and then that will help us determine the limits. So let's go ahead and read the text here. It says, if the graph of a function f of x approaches a horizontal asymptote to the left or the right, then the function is said to have a limit at infinity. If the asymptote is y equals L, then the limit of f of x will equal L. Okay, so plain and simple what this is saying is it says that the end behaviors will give us our limits. Okay, and so to determine these, for large values of x, the highest degree in the numerator and denominator dominate the other terms, and they're the only terms that you need to consider. So when we look at these examples here, I don't care about any of these other terms, right? I care about x to the fourth, and that's it, as well as in the denominator. I only care about x to the fourth. Okay, so what this says here is it says find the horizontal asymptotes. Now, for functions where your powers are equal, what you get, right? So x to the fourth, we're going to cancel x to the fourth. What we get is an asymptote, which is just the coefficients, 5/10, which reduces to 1/2. So here, our horizontal asymptote is at 1/2. Now, moving right along, I'm going to go ahead and look at this case. If I look at this example here, notice again, we don't care about any of these terms, okay? And I have x to the fourth over x to the fifth. So in this case, right, I have a smaller value, little over a bigger example, okay? And in this case, when your denominator gets really, really big, right, bigger than the numerator, okay, we're going to approach 0. So y is equal to 0. That's the little over big. Now, this example is the flip of that, the reciprocal of that. It's the big over the little example. So notice again, I don't care about any of these terms, and my numerator, x to the fourth, is bigger than my denominator. So in this case, what we get is no horizontal asymptote. Okay, no ha, right? So that asymptote does not exist. All right, so let's go ahead. Let's look at calculating some limits. Okay, and what we're going to do here is we're going to consider, again, only the leading terms. So I don't care about any of these terms, right? And I have 5x to the fourth over 10x to the fourth, okay? And in this case, we have a horizontal asymptote at 1/2. So as we go out to infinity, our function is going to approach that asymptote, which is 1/2. Number 10. Here we have the little over the big, okay? And so as we go out to positive infinity, our function is going to approach the vertical asymptote, okay? Which will give us, again, 0, okay? That's the little over big, okay? So the limit there is 0. Now we have the case where we have the limit as x approaches infinity. Okay, and we have 5x to the fourth. Again, we don't care about any of these terms here, over 10x to the third. So my numerator is bigger than my denominator. In this case, our limit does not exist, or it's going to go to positive infinity, right? That numerator is going to dominate, and as I approach infinity, it's going to blow up towards positive infinity. Okay? And here we go. So number 12 is different because the function is factored. So again, what we have to do is we have to make sure we consider our highest degree terms, not the highest degree factors. So what we're going to do is I'm going to consider here 2x, right? That's a leading term, and then I have x squared. So this is 2x, this is x squared, and if I get these, right, this is going to be equal to the limit as x approaches positive infinity of 2x cubed plus some other stuff, some other junk that we don't care about. Okay, now when I look at the denominator, I have 3x squared, and I have an x term here. So 3x squared, that's 9x squared, times x gives us 9x cubed, plus, again, a whole bunch of other stuff. So here I have the powers that are equal, okay? And again, when this happens, we care about the coefficients, 2/9. So the limit in this case is 2/9. All right? So those are rational functions. However, sometimes we get radicals thrown into the mix, okay? And this is important. Radicals frequently have two horizontal asymptotes. So again, what we have to do here, we're going to do some sign analysis, and we'll look at example 13. So in example 13, they want us to find these limits. And again, we don't really care about these terms. Now, what I'm going to do is I'm going to simplify the numerator. So I have the limit as x approaches positive infinity, and what we get is 2 times the absolute value of x. In the denominator, we just have x. So when I plug in infinity into x, I have 2 times the absolute value of infinity. That's going to be a positive value. I hope you would agree. And in the denominator, I plug in infinity, and we get another positive value. So lo and behold, we get a positive. So this is going to approach positive infinity. I'm sorry, not positive infinity. The powers are the same, so it's going to approach 2, and our 2 is going to be positive. Okay, so now when I look at the other end behavior as x approaches negative infinity, again, this is going to be similar to the limit as x approaches negative infinity of 2 times the absolute value of x over x. And so when I plug in negative infinity into my numerator, we get a positive value. When I plug in negative infinity into the denominator, we get a negative. Okay, so this is going to approach -2. All right, in this video, we talked about limits at infinity. And again, remember for rational functions, you have horizontal asymptotes, which your functions will approach at positive and negative infinity. Catch you next time.